Yeah, so good morning, student. So let us start today's discussion. So MA415 Algebra. Okay, and then this is lecture number 15. Okay. Okay. So today we will discuss a very nice class of groups. So we call it P group and nilpotent group. Okay. What is? I will define what is the meaning of nilpotent group. Okay. So P groups we already know. So a group is called P group if the order of that group is some prime power, P power something. Okay, say for example A. Okay, so A is some positive integer. So you can see for you can always choose greater than equal to 1 because for 0 it is identical, right? So some positive integer. So these are P groups. So in P groups has lots of nice properties. And let us try to first understand few of these properties, and then we will come back to those the special definition of nilpotent group. Okay. So let me start with some of the properties of P groups. So so you have a P group and order is P power say A greater than equal to 1. Then this is given to me, and if suppose you have a normal subgroup, say for example I am assuming that H is non-trivial, is a non-trivial normal subgroup of P, then what happened? Then 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 H intersection the center of the P is actually not identity. What does that mean? That means it is not singleton. It has more than one elements. Okay. In particular, in particular, um, if we have a non-subgroup order P, in particular, every normal subgroup of order P, small p, that must be contained in the center. Okay, in JP is contained in the center of the group. Okay, so what does it tells? It tells that null subgroups of a P groups always intersect non-trivially to center. Okay, and the proof is somehow we have discussed before of Cauchy's theorem, but we need to modify a little bit. Now see, H is a normal subgroup, so we can have a map from P cross H to H. Okay, and so you send an element here, so you choose some elements G and some H and send it to G dot H, which is nothing but G H G inverse. Okay, so this is kind of you're saying that P is acting on H via conjugation. Okay, P is acting on H via conjugation, and under this conjugation what happens? So you can use this orbit stabilizer formula, then then the orbit stabilizer formula becomes, how does this orbital formula becomes? It becomes like this. So you have the set H, you want to count the number of elements here, and that will be you remember the fixed set of the group G here. G is nothing but the P group P, and that will be actually nothing but H intersection the center. Okay, and then the rest is already cardinality of P, and then you have those centralizer of those elements, say AI, and this what are AIs? So AIs are those such that the centralizer of AI is not equal to the full group P, and these are distinct representative. Something say, um, I mean, this is a little bit right on the start that we already discussed about time, right? The distinct representative of those things. And when you have those classes which are singleton classes, those will be inside this. Okay, so you can write down this by these. Okay. Um, now, now you see that H P, say P group, so order of H divides order of P, right? Lagrange's theorem, and hence order of H will be some kind of P power something alpha. Okay. So P divides left hand side, so P divides order of H, and also P divides the sum. P divides the full sum, right? That is cardinality of centralizer. This thing we have done several times though, and then hence this implies that P divides this order of this. Clear? So what does that mean? That means this H intersection GP, it is always non-trivial. The proofs are similar to the proofs of that the center is non-trivial. So it's kind of intersection in the center. Okay. Okay. So then, so in particular, when in particular, if H has cardinality P, right? For what we asked, we said that every null subgroup of order P is contained in center. So H is cardinality P means what? That means so you also know that the center is trivial, right? Then we already know that the center of this P group is trivial, right? And if H is P groups, then H intersection this is also at least P, right? So what does that mean? That means this implies that H is a subgroup of P, right? This is clear? So this is non-trivial, we just prove it. So what does that mean? That means an H can be at most P, so the intersection cannot be more than P, right? So the intersection has to be P. So this H intersection, that must be, the cardinality has to be equal to P, which is nothing but cardinality of H, right? So that means H is a subgroup of sitting inside Z not Z. Okay. So every null subgroup whose order is P is inside center. It means central subgroup. Okay. Yeah. So this is one important observation. Another important observation we should discuss, that is, suppose you have a null subgroup, for example H is a null subgroup of P, and then H contains what it contains a subgroup of order p power something say b for every p power b divides the order of the group H. Okay, so what does that mean? That means whenever any p power b divides um, okay, not only that, so this also is subgroup of order b for this, which is normal. Yeah, so this is important, which is normal in p. So what does that mean? That means so whenever you have a normal subgroup which of a p group p, then normal subgroup contains obviously that subgroup is also p group, and whatever the prime divisor divides the order of the subgroup normal subgroup H, you have a subgroup of H which is normal subgroup inside p of same order. So in particular, you can say that in particular, when you choose H equal to p, then what happens? Then in particular P has a normal subgroup, normal subgroup. P has a normal subgroup of order p power b for every such b. So what does that mean? For 0 less than equal to b less than equal to say a. Okay. Remember order of p equal to, yeah, so that is given, is order of p. I assume that this is some prime power a. So okay, so the proof is also so induction. So the similar proof we use in to prove Silo's theorem. Remember, similar way we can prove it. I will just give you the that sketch of the proof. I think you can prove later. Okay, uh, so what happen if this is equal to so p. So I mean I will say the a equal to say a equal to 1 in the case, or say a is a subgroup with single element. Okay, then it is trivial, right? Then there is nothing to prove, because if p is a p is already is p, then only subgroup of p power b is in identity, right? P power 0. So we know that. Okay, then there is nothing to prove. Okay, now let us assume that it is true. Now let us assume that the statement is true for yeah, so uh, um, for any such for any group uh, with order less than order of p. Okay, this is my induction hypothesis. Okay, so now how do I go further? Now now assume that so a greater than 1 and h is not trivial, non-trivial normal subgroup. then what happens? Then we know that previous theorem tells me that edge intersection center is non-trivial, right? So when I'm saying this in one, I mean non-trivial. So the cardinality is bigger than one. Either I will write down this notation. So both are same meaning. This means this is that is edge intersection center is non-trivial. Okay. So what does that mean? That means um, so this is a P group and it is more than one. So hence Cauchy's theorem tells me. Hence, so what does Cauchy's theorem tells me? U is missing here. Cauchy's theorem. Hence by Cauchy's theorem there exists a normal subgroup. Okay. So N of P such that. Yeah, so why I am saying null subgroup? Because any central subgroup is null subgroup. We already proved, right? So this N is sitting inside H intersection Z mod PZ. So what does that mean? That means N is sitting inside the center. So this is null subgroup of the original group P. Okay, of order order of N equal to P, because P divides that order of H intersection ZP. So you'll have an element of order P and then you take the cyclic subgenerated by that element, that will be the N. Okay. So I have a null subgroup order P, so I can go modulo. The proof is, you remember the proof of Shallows theorem? So similar thing, right? So we can go modulo um, this P bar, which is P mod N, right? Now you see that P bar is now has order P power A minus 1, so which is less than order of P, right? So you can use induction hypothesis here. Okay, so here what happened here you have H bar is sitting inside P bar and it's also an order subgroup, right? H is an order subgroup of P, so H bar is an order subgroup of P bar, and order of P bar is less than order of P, so you have induction hypothesis. So therefore using induction hypothesis, what will get? So you'll have that H bar contains for every uh, let's say divisor, every P power B divides this. Okay, there is a subgroup. There is a subgroup. Say for example, let me write down K bar. So this is in quotient group, so I am writing bar here. K bar of H bar. Okay, K bar of H bar, which is normal in P bar, and the order is what? Order is also P power B. That was the induction hypothesis. Clear? So for H bar you get by induction hypothesis something K bar, which is this, right? But you remember this fourth isomorphism theorem or whatever the correspondence theorem. But uh, so by correspondence theorem, you remember there is one-to-one correspondence between the subgroup of P mod N and subgroup of P containing N, right? So correspondence theorem, there exists this K actually containing N, such that this K bar equal to K mod N, right? And thus what is K bar? So K bar will be a conductor will be what? Will be equal to p power p minus p plus 1. So induction hypothesis, you just prove it that if there is a from yeah. So okay. So this is the proof that um, you have a subgroup of this, and also you can ask why k is normal. So that is obvious. So I'm leaving you as a proof that, see, you know that k bar is normal, right? N is normal. Now can you prove that k bar is normal? So your this k is nothing but uh, direct product of, you can write down this direct product of this. Okay, this is also normal to p. Okay. Yeah, so now when so in particular when you choose h equal to p, then what happen for every proper divisor p power b, we divide the order of the p you have, and the statement is true. What does that mean? That means you have a null subgroup of order p power b, statement is true. Clear? So this completes the proof. Okay, so um, yeah, so now we need to prove one more thing. Uh, so this is maybe theorem 3. Yeah. So suppose now you have a subgroup, only subgroup, say, which is subgroup of p, and then what happen? So inside p, subgroup of p, then okay. So this is, let me write down proper subgroup. Suppose H is a proper subgroup of p, then H is always a proper subgroup of the normalizer of H in P. Okay, so what does that mean? That is this, what I'm saying, that every proper subgroup of P is a proper subgroup of subgroup of its normalizer in P. Normalizer in P. Okay, so whenever you have a proper subgroup inside a P group, the normalizer strictly contains that subgroup. Okay, and so the proof is also in the similar line. Okay, there are small tricks, so let us try to understand that. So again, so we will use the induction. So induction on that order of the group. Okay. Um, so what happen if like order is p square? Okay, so or p, if order of p equal to p or p square, then what happen? We know that then p is abelian, right? That is for sure. For p it is actually cyclic, but I don't care. Cyclic groups are also abelian groups, so abelian, right? And what does that mean? So abelian means what? Every subgroup is normal subgroup, right? So and the result is trivial. So every subgroup normal subgroup means normalizer will be full thing, right? Uh, then every subgroup of P is normal, and thus we have the proof, right? Because then the normalizer will be the full group P, and that the original subgroup is contained properly inside the full group. Okay. Now, so what does that mean? That means I need to assume that. So now, so let us assume that order of P is strictly P square, right? And uh, and this is my assumption, and we have a subgroup P which is strictly a proper subgroup, so proper subgroup of P. Okay. Now see, what does the center do? Center of this group that commutes with every element, right? So center normalizes every subgroup of P, right? So what does that mean? That means so now see the center of the P, it is sitting inside the normalizer of P and H in P. Why? Because yeah, so because as um, this center normalizes every subgroup, right? Whatever subgroup you choose, that will be normalized to center. Okay. And also, you know, the center is non-trivial, so center is also non-trivial. That also, you know that. So you have a non-trivial center sitting inside this. Okay. Now there are two conditions. So the center may not be contained in H. Then what happens? So if the center is not inside H, then what happens? Then 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 you consider another, say, H prime is the smallest subgroup generated by H and the center. Okay, H5 then contains H, right? You have a subgroup which contains H. Okay, so this is okay to everyone. So there might be case that the center is not contained in H, and then H is properly contained in that H prime. Okay, and mm, uh, and what is H prime? So H prime is also okay. Yeah, so I should say properly. This is properly because it is bigger than H, right? But this is what this is also. So H is sitting inside is properly inside H prime. H5 is sitting inside the normalizer of P in H, right? Because H normalizes H, center normalizes H, so H dash normalizes H, and hence we're done. So thus H is sitting inside properly normalizer of P inside H. This is one case. Okay. So the what is the other case? Other case is that center inside the H. Now if the center is inside the H, then what happens? Uh, then again, you know that center is non-subgroup, right? So again, you go to that P bar, which is P mod the center. Okay, and this is again this order of P bar is less than order of P, right? What does that mean? That means you can use the induction hypothesis here, right? So induction hypothesis tells you that you have okay. So let me write down that. Um, so and you write down that each bar is H bar equal to H mod the center. Okay, so this is subgroup of P bar. Clear? So now you have H bar and P bar, and you know that H bar is properly contained in P bar. Why? This is homework. This is do it. If H is properly contained in P, the H bar is properly contained in P bar. You do it. Okay. So you can talk about uh, index hypothesis. So index hypothesis tells you that because the order of a P bar is less than order of P, then H prime that is properly contained in the normalizer of H prime inside P bar, right? Because now I am inside P bar in the group P bar. Clear? This is I think obvious. Now, now what does that mean? Uh, so now you need to. So now only thing you need to prove that this. This is a subgroup inside P bar, right? Subgroup inside P bar. So we need to now prove that. So again in that correspondence theorem, what does that do? Correspondence theorem implies. So we have age, uh, so that non-answer of H prime in P prime. So this is nothing but some subgroup, right? So what is that? So this is actually this implies this. Okay, prove it. Homework. This subgroup is actually nothing but quotient of this. Okay, and the proof is again obvious. Yeah, okay. So why don't you prove it? Why don't you prove it that first of all this contains the center. That is not a problem, right? And what you need to prove that? You need to prove that if you have something which normalizes H bar in P bar, then that element also normalizes H in P. Okay, so this is proof simple. Okay, so if uh, something H plus H ZP or rather AZP, I should write down. AZP normalizes H bar in P bar, then A normalizes H in P. Okay, this proof is simple, you do it. Okay, and again from here, because this is a proper subgroup from index hypothesis, then again thus you will have H is a proper subgroup of normalizer of H in P. Okay, this is actually the proof. So whenever you choose a P group, then every proper subgroup is actually sitting inside the normalizer properly inside the normalizer. So what does that mean? Normalizer of the proper subgroup is bigger than the normal subgroup. That subgroup. Okay. Okay, and then there is one more important idea. So before that, let me define one more thing. So something called uh, maximal subgroup. So what is a maximal subgroup? So a maximal um, subgroup, say of a group G uh, is a proper subgroup uh, M of G such that what happened? Such that um, there is no proper subgroup, no, or rather, I should say, yeah, so no subgroup H, no H, G, such that with M is sitting properly inside H and is sitting inside G. So what does that mean? That means that if this kind of thing happened, if M is sitting inside H, this cannot happen. So what does that mean? That means if M is sitting kind of, so this is strict notation. So what does that mean? Then either M equal to H or H equal to G. Clear? In this case, if you have a subgroup that contains M by this, then either M equal to H or H equal to G. So it cannot be sitting inside properly inside another subgroup which is also proper in G. Okay, so this kind of subgroups are called maximal subgroup of that group G, and that exists obviously. Yeah, so we can have a theorem that every maximal subgroups of every group, every maximal subgroup of a P group P has index P and it is also normal and also normal in P. Okay, so maximal subgroups are P groups are having index P, and there are also normal subgroups inside the P group P. Now, how to prove this kind of statement? So okay, so proofs is simple, not difficult. So let me give you an idea. So suppose you have a maximal subgroup. So M is maximal subgroup. So M is strict proper subgroup of this, and we know that whenever you have a by previous theorem that for every subgroup it is actually contained inside the normalizer, right? Normalizer of M inside P. Okay. So what does that mean? That means this implies that it has to be uh, this has to be equal to P itself. Okay. And what does that mean? That means that see, this normalizer is full group, so that means that M is normal subgroup inside P. Clear? Okay, so we have that whenever you have maximum subgroup, it becomes a normal subgroup, and then you can talk about the quotient group. Quotient group P mod M. P mod M is a quotient group, right? Is the quotient group, right? Now the question is that what is the order of this quotient group? So quotient group which is also a P group, which is also a P group. Okay, because this is also a P group, so it has order some P power say beta or something, right? So you can have that the P bar has order some P power some beta. My question is that can this beta bigger than 1 or not? Okay, so now claim uh, this beta has to be equal to 1. Why? If beta bigger than 1, then we just prove that there is a proper subgroup. Okay, so if beta is greater than 1, then what happens? Then there exists a proper subgroup, a, a proper subgroup of P bar contains or containing proper subgroup of P bar. Okay, so I should say order of order say Proper subgroup of p verbs of order say uh, p order greater than p, right? Greater than equal to p is there, right? So whenever you have proper subgroup order greater than equal to p, so what does that mean? So that will be something. So that is um, you have something, say, what to write down, say q. So this is or rather q bar. So this is a subgroup of p bar such that its order is at least p, right? And q bar will be a subgroup of p bar, which is nothing but p mod n, right? So again, thus uh, uh, correspondence theorem, um, correspondence theorem implies, what does it implies? It implies that this q is nothing but you have there exists q subgroup of p such that q equal to q bar is sorry q uh, should write that the other way, that q bar is nothing but q mod m, right? So q bar is subgroup of p bar, and hence you have a subgroup of p containing m, that is q. So q bar uh, m is properly contains q as order of q bar is at least p greater than 1, right? Clear? So what does that mean? It's not possible because yeah. So again, I am assuming that, okay. So let me assume that um, proper subgroup. Yeah. So this is proper subgroup. I assume already. Yeah. So this q bar is a proper subgroup of p bar. So what does that mean? That means q is a proper subgroup. Q is a proper subgroup of p. So q cannot be full thing, right? So this is inside p. So thus, so this is a contradiction. So this is a contradiction to the fact that um, M is a maximal subgroup of P. Okay. So what does that mean? That means beta equal to 1, and hence uh, this P bar, uh, the order is yeah. So this is this order of this is equal to P only. See, this cannot be 1. If it is 1, then M is not a maximum subgroup, right? M is a proper subgroup. So index of M inside P is the prime P. So this completes the proof. This completes the proof. Okay. So maybe I should stop here because if I have to define what is a for example nilpotent group, then it will take some more time. So let me just stop here, and maybe in next class we will discuss what is a nilpotent group. Okay. Okay. So